Hello, and thank you very much for coming today. I am Susanne Schwenzer. I'm a professor of planetary mineralogy here, and some of you might have seen me orbiting Mars today. But that's not the most important part. There are two things that I want to say before I introduce the most important parts. And the one is I want to thank all the volunteers from the Open University, including Sam hiding behind the screen, to make this event possible by doing all the things behind the scenes. So please give all the Open University volunteers a round of applause. But we also have people in blue and pink shirts, and they are the volunteers and the staff from the IF Festival. And without them, we couldn't do this either. So another big thank you and round of applause for all of them, please. And now, with no further ado, it is my greatest pleasure to introduce Dr. Elliot Sefton-Nash to me. Welcome, Elliot, to the Open University. And we are especially grateful for you to be here. Come on out. we both. Elliot, you are interrupting your holiday to be here today, so thank you very much for that, and I know you have a lot of interesting things to say. First of all, let me say you got your first degree from almost here, University College London, and you got an undergraduate degree in Planetary Science, and that is also a Master of Science in Planetary Science. And then you went to the University of Bristol, so he's a real Brit, did everything here. And that was in planetary geology and remote sensing with Professor David Catling, which some of us who work on Mars and Martian atmospheres knows really well. And that was water-altered mineralogy and the landforms in equatorial regions of Mars. So all the little snake features you might have seen on the globe, he knows a lot more about them. So you stayed at Bristol for a little while, did a postdoc there, and then went to Caltech in California, University of California, Los Angeles. That's actually UCLA. Use the abbreviations you know, Susanne. So the NASA, and you worked on the NASA Lunar Reconnaissance Orbiter, and on the radiometer experiment, and studied lunar polar volatiles. So water never left your thinking, right? And to constrain the abundance of water, ice in the lunar south polar region. And then you came back to the UK, to Birkbeck, and you started working on what you will talk about today, the ESA ExoMars rover. And you tried to select the landing site, and you were eventually successful at selecting Oxyaplanum as the landing site. And I am sure we hear some about that today too. And in 2016, the final destination, ESA, and that's where he is coming from today. And you are working on the ExoMars Rosalind Franklin rover, and that's the Mars part. And there's also a little bit of sample return, where I think it's the two things where we met, the ExoMars rover and the sample return. And then it's also the JAXA Martian Moons Explorer. Mars has two moons, Phobos and Deimos. And so if you want to know anything about it, don't ask me, don't ask Elliot. And you are a prospect scientist as well. There are two awards that I want to mention. That is in 2013, the NASA Group Achievement Award for the Divina Lunar Radiometer Science Mission Team. And in 2023, the ESA Teamwork Excellence Award for the ExoMars Rosalind Franklin Mission Team. And now, with no further ado, I leave the stage to you. Tell us all about ExoMars.
All right. Thank you so much, Susanna. That was a fantastic introduction. I certainly did not expect it, but many thanks. It's a pleasure to be here. Many thanks to all of you for bringing yourselves here, and a special thanks to the OU team for making this all happen. I have visited the OU many times, and I'm sure as many of you know, it's really a world-class research institute as well as a distance learning institution. And in particular, there's a lot of space science that happens here. So you've probably seen the models of spacecraft out in the atrium. But let it be known that we should really be proud of what happens at the OU in terms of space science. So this is a talk of three parts. I first want to tell you what is ESA, what is that about, because it may not be completely familiar to you. This is the European Space Agency. Next, I want to talk about this, Mars, and how it preserves a record of everything that has happened to it since its formation. And last, I'll talk about the upcoming mission, the ExoMars Rosalind Franklin mission, which is to do with the ExoMars. It's a program with 2 missions. The rover is the second mission. The first mission is the ExoMars 2016 mission, which if you came in through the upstairs atrium, you would have seen a model of the trace gas orbiter. That was the first mission. So it's a 2-part recipe. So first, what is ESA? So ESA, I think if I show the corporate slides, this is the message that we like to project, that we committed to the peaceful exploration and use of space for the benefit of people, for society and for our planet, of course. And note this is peaceful, this is civil space, we don't do anything related to defense, and so this is, in some way a real kind of something that we can work for societal benefit. Just in some kind of summary numbers, we have 23 what are called member states. This is 23 individual countries who sign up to ESA because they want to do space exploration. And they recognize that they can together accomplish much more than they could do on their own with their own space agencies. The UK is one of those members, of course. ESA has about 2,500 staff members. But there are, of course, many more people working in ESA, so 6,000, more than 6,000, including contractors and research students and other experts. We have a headquarters in Paris, but we also have a lot of other sites around Europe, including one in the UK, in Harwell, called EXAT. And the budget is roughly 7.8 billion this year, but the tagline that we like to communicate is that's about a cinema ticket. I hope it's not more expensive than that, given inflation recently, but that's a rough estimate of how much it costs, the taxpayer to be involved in space exploration. ESA is made up of a bunch of programs, and the programs each contain missions and research activities related to those missions. They're broadly divided into directorates. The part that I'm most interested in and where I work is over here in science, but also in human and robotic exploration, which is where the ExoMars program lives. There are, of course, directorates to do with rockets. We have to get to space somehow, so we have a whole directorate related to space transportation that procures and designs rockets. Operations, how do we fly the spacecraft? Technology development to do so. And a bunch of other programs which are, relating to the safety and the well-being of our planet, so Earth observation, navigation. The GPS on your phone very likely uses the Galileo network, which is run by ESA. And some other things relating to space safety in particular, which is a fun highlight, quite a recent addition, which gives us early warning systems for things like space weather when the sun is behaving badly, or if there are asteroids where we think they might collide with Earth. But in terms of science, just to show a few highlights, and also to point out that most of ESA's flagship science missions have tended to be space-based, right? Of course, not on the Earth, in space. It's actually not that common to talk about a mission that is landing on the surface of another planet or another body. And so these pictures here show you missions that are really to do with investigating our own sun, the Jupiter system, the Jupiter Isomunes Explorer, JUICE, Gaia, an astrophysical observatory, which is mapping 1 billion stars in our galaxy, and an interesting mission that's under development, Euclid, which is exploring the dark and early universe. So if you plot all of the missions that relate to ESA's science and robotic exploration programs, you can show them nicely as a function of where they're going and when they're launching. And these are just a few of the solar system explorers, going right from observing the sun to the outer solar system. Cassini-Huygens, which investigated the Saturn system, is way over here, and we had the Huygens descent probe on that mission. But of course, there are also astrophysical and astronomical observatories in space, because space is a very good place to observe the distant universe. You don't have a pesky atmosphere in the way, so you get a clear line of sight to things that are far away. And you can look in a lot of different parts of the spectrum, so all the way from the infrared microwaves out to gamma rays, very high energy, short wavelength photons. And recently, based on discovery of gravitational waves, we're developing missions to measure gravitational waves, which detect things like merging of giant black holes far away in the cosmos. So this is a really comprehensive science program that covers a whole bunch of different things. Just a quick highlight from Earth observation. If you plot all those similar, in a similar style, the missions that we're using to observe the Earth, you could divide them roughly into things that are for science, things that are for part of the EU's Copernicus program, which is an Earth observation program funded by the EU. And of course, it's a huge swarm of missions there. And also meteorology, so things like observing the weather, forecasting, and so on. And there's another agency called EUMETSAT, which we work with to operate their missions. So there's really a lot going on. I mentioned before navigation, Galileo, the most recent addition to the global navigation suite of constellations. This is something the EU pay for, but ESA deploy in a way. And so far, we think it's serving about 4 billion people who use it on their phones. So this is all very kind of permeating modern life. And one interesting recent addition is space safety, where we monitor things like the solar wind as it constantly bombards the planets. We monitor asteroids, new objects detected that are approaching Earth that have some possibility of impacting Earth, usually very low, but we of course track them, detect them, and try to project whether they present a risk or not. One recent highlight mission for this is the Hera mission, which is actually humankind's first attempt to try and divert the trajectory of an asteroid. So if you recall the 90s movie Armageddon, this is essentially the real version of that, but it doesn't involve a ragtag team of oil rig workers. We also have a Ramesses mission, which will intercept the Apophis asteroid as it passes by us in 2029. This is the asteroid that's currently known to have the highest probability of impacting Earth, but it's still extremely low. And as we get closer to that time of its closest pass, its closest flyby, we will know for certain, of course, that it's not going to hit Earth. But we want to get as close as we possibly can to it with a spacecraft to try and observe it, try and understand where it's from, what it's made of, and so on. We also have astronauts, as you probably expect, including Rosemary Coogan, British astronaut, and they often fly to the International Space Station. This is a very international project, of course, between Europe, Japan, Russia, Canada, and the US. It's been going a very long time, and it's produced a lot of great science, a lot of public outreach, because astronauts are people that they are superhumans. Having met a few of them at this point through work, they're really just incredible people. So it's fantastic to have that kind of expertise available to send to space and do really useful stuff. We also have missions to the moon. We're involved with NASA's Artemis program, and eventually European astronauts will be going back to the moon as part of that cooperation. And of course, beyond the operational lifetime of the International Space Station, we also have the next generation of space stations, which is called the Gateway, and we're contributing some elements of that habitation module, the communications, and another kind of viewing module. The one on the ISS is called the cupola, and there's a module attached to it, but this is another element that we're supporting. And we also have this thing called Argonaut, which is a large lunar lander which can deliver tons of payload to the lunar surface in the future. So these are all exciting things to come, and what I will focus on as the third part of my talk is the Rosalind Franklin mission. Of course, this is very close to my heart, and essentially the reason that I came to ESA in the first place 9 years ago now. I won't give away too much before I get to that section. But just to tell you that we have a lot of sites around Europe, including a spaceport in French Guiana, where we launch our European missions together with our partner, the French space agency CNES, who coordinate the launches because it's on French territory, French Guiana. And where I work is actually called ESTEC, which is in the Netherlands. This is the Space Research and Technology Center. It's the largest ESA site, has a few thousand people. And it's where we do most of the design, the development, and a lot of the management of the missions. So I can tell you my office is about here. And this is ESTEC. If you ever get a chance to visit, please do. We also have an outreach center there, so it's really worth a visit. There's a fantastic museum in Space Expo just over here. And it's a nice reason to visit the Dutch coast. The beach is just past the dunes up here. It's a pleasant trip. So, as I mentioned, there's a lot of stuff going on there, but most importantly, we have facilities to do the acceptance of missions. So when we pay the aeronautical industry to develop a spacecraft, they deliver it to us, and we have to make sure it works. And so we have a large suite of testing facilities, which is over here, including a space simulator and other chambers for acoustic testing, electromagnetic testing, and there are various technical labs related to the development and management. So, for example, the propulsion lab is one example of those. So all this is kind of the background of where I'm coming from, and just also to give you some encouragement. If you're interested or working in any of these domains, or you know people who do, we have a lot of jobs available. So please do distribute, jobs.esa.int amongst your family, friends, colleagues, and if people are interested, please take a look. There are also a good number of opportunities for early career folks. There are internships every year. They can be up to 6 months, I think. Graduate trainee program, which is kind of a master's level first job type thing. National trainee programs. There's a fellowship program for people who've completed a PhD. And we also support co-funding of research. So if there are people doing research who would like it to be supported by ESA, and there's a connection to what ESA's doing, that's something that can be supported. And we also have a new junior professional program, which is kind of an initial 4-year job, which then leads to a permanent position. So circulate the word. I would greatly appreciate it. And thanks for taking a look if you do. Now to the interesting part. So what I wanted to do in this second section is really talk about the namesake of the talk. So a world record. It's a little wordplay, but what I mean is that Mars is a place which is literally a record of its own history. The surface, the interior, the atmosphere are the result of billions of years of planetary evolution. And one of the exciting things about Mars is that because the most recent period on Mars has been relatively quiet compared to its past, a lot of its early history is very well preserved in the rocks on the surface. And this gives us a great chance to explore and understand what the early solar system was like, and indeed what Mars was like, and if it was potentially like Earth at that point in history. So this is what I really want to touch on. I'll go into a bit about what we've learned from recent missions, and then of course look forward to future missions. But first, a few comparisons. So many of you may know Mars is a little bit different. It's smaller than Earth. It has a day length that's actually very similar to Earth's. It's just a little bit longer, 24.7 hours. It has a very similar axial tilt. The year is twice as long, though, more or less. Gravity is, of course, much less, and because it's further away from the sun, we don't get as much sunlight, so there's less energy overall, which reaches the surface. The atmosphere is rather different to Earth's. Mars is mostly CO2, a little bit of nitrogen, and just a sprinkling of oxygen and argon and water. And of course, on Earth, this is very different because we have mostly nitrogen. But the biggest difference is the atmospheric pressure is so much lower on Mars. Today, it's about 7 millibars, whereas on Earth, of course, we have 1,000 millibars. And this has a dramatic effect on the processes on the surface and how the atmosphere produces those and interacts with the surface. So some other big factors where Earth and Mars differ are, number one, the magnetosphere. So this is a magnetic field that surrounds the planet, and on Earth, we have one. It's generated by interactions between the core and the lower mantle. This is the interior of the Earth, I think, or perhaps the core boundary between the solid and the liquid part of the core. I'm not an expert in that field, but in any case, it's called a dynamo, and it generates a magnetic field which protects our planet from particles which interact with it as they approach the Earth. On Mars, there is nothing like that today. The only magnetic field on Mars is very weak because it's the result of remnant magnetization of minerals in the crust, which were formed when there was a magnetic field in the past. And so that means that a lot of things that don't reach Earth's surface because we have a magnetic field do reach Mars's surface, and that has an effect on the atmosphere, but also on the surface. Plate tectonics. We, of course, have active plate tectonics. We live on the crust, and the crust is divided into plates on the Earth, and those gradually recycle, and new crust is produced at mid-ocean ridges and in volcanic hotspots. And so on Mars, we don't see any evidence of plate tectonics. That means that Mars's crust is not being recycled. So what's there now was probably there billions of years ago as well. Plate tectonics has an important role on Earth, and that is to close the carbon cycle. So on Earth, minerals that are deposited in the crust are capturing carbon from the atmosphere, CO2, and as that gets subducted through the subduction of the lithospheric plates, that carbon is then released again through volcanism. But that recycling process doesn't happen on Mars. Mars also doesn't have large moons. It has two very small moons presently, Phobos and Deimos, but we have a very large moon in the Earth, and one of the impacts that has is to stabilize Earth's axial tilt. So that means that Mars's axial tilt is free to wobble as much as it likes. And in fact, a few good studies have shown that even in the past few million years, and that seems like a long time, but geologically it's the blink of an eye, the axis has wobbled around quite dramatically. Now, what does that mean? That means that the climate in any location on Mars has probably changed a lot in the last few million years. So the ice caps will have had different locations. The seasonality of the temperatures is completely different depending on which point in history you're looking at. And so this has a big effect on the evolution of the surface over time, because different things are happening according to climate. We think about on Earth, our ice caps now are where they are, and they have been for a long time. But on Mars, that's not necessarily the case. And of course, the big one, liquid water. Earth has abundant liquid water, as evidenced by the last few days if you've been outside. Mars, not so much today, but there probably was a lot more in the past. So let's take a step back and look at the bigger picture. And one important concept, especially as we are discovering more planets out there in the universe, exoplanets, what we like to think about is the concept of a habitable zone. So where is something potentially habitable for life? If we just plot the first few planets in our solar system, we can calculate what's called the equilibrium temperature. This is the temperature you would expect the planet to be based on how far it is from the sun. You could do this for any planet, any star, based on its size and brightness. And so if you calculate this, you end up with a temperature in which you would expect the planet to live. It would be roughly near that point. And you can also then plot the range in which you would expect liquid water to be liquid rather than being ice or being water vapor. And so if you do that as a very simple case within the solar system, you plot something roughly from just past Earth towards Mercury, where you would expect liquid water to be in its liquid form. However, of course, we know that not really to be true. The equilibrium temperatures of Mercury, Venus, and Earth, and this is also factoring in there what's called the albedo. So effectively, what color is it? Brighter things reflect more sunlight, so ultimately retain less energy. This means that Venus is much colder in equilibrium temperature than you might think, 229 Kelvin. That's pretty cold. Remember, 273 Kelvin is 0 degrees Celsius. But Venus, of course, is not 0 degrees Celsius. It's much, much hotter than that. And that's because of the atmosphere. And so what you end up with is the actual temperatures being very different from the equilibrium temperatures. And this is true for Earth, too. So we can plot 288 Kelvin. That's the actual temperature, roughly 15 degrees Celsius on average. But the equilibrium temperature, based on how bright Earth is actually much less than that. Now, for Mars, you might notice that the equilibrium and actual temperatures are the same number. This is because Mars has an extremely thin atmosphere. And so the insulating effect of the atmosphere is very small on Mars. So plotting all of these things, what you can do is think about what that means for a habitable zone. And so a habitable zone is the zone within any star system where life may be able to survive and perhaps even originate, start to form. But this is dependent on a lot of things because things like greenhouse gases, so water and CO2, and also methane, it's a very strong greenhouse gas, can influence what the actual temperature of the planet is. And we see that on Earth, of course, increasingly so these days. The carbonate-silicate cycle, so this is how the rocks are interacted with the atmosphere, how they are then subducted into the crust and recycled, releasing more CO2. So on Earth, remember, we have plate tectonics. This is a big factor in governing our climate. On Mars, not the case. And there are other things like modifiers, like clouds. If you have white clouds, they can reflect a lot of sunlight, and so then less energy reaches the surface, so the planet maybe stays a bit cooler. This is what happened. This is what would have happened on Venus if it was white, but in fact, after all, the atmosphere is very, very thick and retains a lot of heat. And what happened on Venus is essentially a runaway greenhouse effect, where the atmosphere is in a positive feedback loop, and then it reaches some equilibrium state at much higher temperatures. So what we can then plot is something like a reasonable guess at a habitable zone in our solar system. And if we do that with all these factors considered, we get something like from Earth, roughly out to Mars, based on what we know about where life survives today, the life that we know about. But you might consider extending that a little bit, an optimistic habitable zone, if you consider things like extremophiles. These are organisms that live in very extreme places, the bottom of oceans, or they're in Antarctica or so on. They might not have evolved there, but they can survive there. So we don't know the full extent of what's possible. We only know what exists on Earth, right? And so based on that judgment, we can say this is an optimistic habitable zone that does include present-day Mars. So Mars today is not a pleasant place to be, although very interesting. It's an extremely dry and cold place. It has a very thin atmosphere, of course, so all the stuff that's coming from out there in the cosmos will eventually reach you on the surface. There's dust everywhere, and not just the dust that we get on Earth, but dust that is extremely fine-grained, which can be a problem if you breathe it in. It's a very, sharp particles which have not been eroded down, by all the processes that we have on Earth, like a thick atmosphere and biology, which, have a lot of activity, which means that sharp things eventually become blunt. So think of rounded pebbles on a beach, for example. That happens less so on Mars. And so all the dust is still sharp, and it can really be a problem for astronauts in the future. It has very high ultraviolet radiation from the sun. Mars is further away from the sun, so ultimately it receives less of it. But having a much thinner atmosphere means that what does get there, pretty much all of it reaches the surface. And this is very bad for organic molecules and life, because ultraviolet can, of course, damage our skin when we get sunburn and break down the bonds in organic molecules. And so this is bad for not only ultraviolet, but also for ionizing radiation, which comes from out there in the cosmos due to high-energy astrophysical events that throw energetic particles at us constantly. But what do we know about present-day Mars? And why do we know it? And the reason is that we have some fantastic spacecraft. And in fact, this is ExoMars Trace Gas Orbiter, which you will have seen a model of out there in the foyer. And in the last few decades, we've really had a big change in our understanding of the surface, which is driving a lot of new mission ideas and proposals. So this big step change, I'll try to illustrate with a few pictures. This is one taken by the Viking 2 orbiter, I believe, in the 70s. And it's of a place on Mars which we have now imaged in much greater detail. This is Argyll Basin, which you can try and identify later on the globe. But at the western edge of this is a place called Hook Crater. This is another impact crater just on the edge. And if you look at more recent images since Viking, this is the same frame. This is the square that I highlighted. This is Hook Crater as imaged by Mars Express, a spacecraft that was launched by ESA in 2003. And that contains an instrument called the High Resolution Stereo Camera, which has made fantastic maps of the surface. And notice the scale up here, if you can read it, it's 50 kilometers. So this is still big, right? I mean, this crater is 50 kilometers across-ish. It looks a bit weird in my perspective from the podium, but you get the picture. But the point is, we can do much better than that. And in fact, we have produced a lot more images than this in the past. You might have noticed this little rectangle appear down here. This is an image taken by Trace Gas Orbiter Cassis, which, of course, is on the spacecraft out there in the lobby. This is that very same area shown in that little rectangle, zoomed in, and we scroll across it, and what we see is the finest detail that you might wish to look at if you were trying to interpret the geology on the surface from orbit. We can do one better than this, by the way, but I'll get to that later. So what you're seeing here are the ripples. These are formed by the wind, and they're typically transverse, so the wind would be blowing left to right in this picture, and you get these ripples. They change a bit because the wind is blowing around these mounds. And these dark tracks are actually dust devil tracks. The dust devils are kind of like mini tornadoes that happen in the Martian atmosphere, but they stir up the material on the surface, and so the material reflects light differently, and in these images at least, they appear darker and a bit bluer. And so this is very exciting because it shows that Mars is active today. Things are changing all the time, albeit a bit more slowly and less frequently than they do here on the Earth. If we look somewhere else on Mars, we can look at the polar regions. We look at layered deposits. Remember what I said about obliquity cycles, where Mars's axial obliquity is moving back and forth. Well, because of those cycles, it's believed that these layers are forming as a function of those cycles, and they gradually accumulate and get eroded in check with those timelines. And so this is a way where we can really probe the record of Mars's history and try to deconvolve, what exactly happened and when. And the geology is right there for our taking. So the message here is that it's all there on the surface, and while Mars today is active and things are changing, the time when things changed the most and were most similar to Earth and were most relevant to habitability questions that we have is in the past more than 3 to 4.5-ish billion years ago. And this is what I'll talk about a bit more in the next few slides. So Mars today, pretty cold, pretty arid, and wind sculpted, essentially. The activity that we see on the surface is based on small seasonal changes in volatiles. So this is water and CO2 ice that are trapped in the small polar caps on Mars that evaporate and then condense. And in some places, they're buried in the subsurface. What you see here is a picture of a very dark dune, but with these white patches. And the white patches are actually seen to change, and things seem to be kind of flowing out of them as this ice sublimes away into the atmosphere. So in many cases on Mars, because Mars's conditions are close to what's called the triple point of water, so it can be a vapor, a solid, or a liquid, that means that quite often, if there is an exposure of water ice, it will just sublime away to a vapor. It doesn't melt. And anyway, these processes cause things to happen on the surface where activity can be observed. And now with these most high-resolution cameras that we have, we can see those things happening from time to time. So this is a good indication of what's happening today. This most recent period of Mars's history is called the Amazonian, and it's lasted about 3 billion years. So it's not a short thing. And 3 billion years is almost all of Earth's history that we know about, essentially. There are a few things that are left on Earth that are older than that, but not so many, because Earth is so dynamic. The crust is recycled, the atmosphere is thick, there's a lot of water. Essentially, the ancient history of Earth has been erased by its own surface processes. On Mars, as I mentioned, that's not the case. And so we can see a lot of evidence of those time periods from a few things, and I'll touch on these three. So the first one is water-influenced landscapes. As you can see on the globe outside, there are places on Mars which have giant channels. And of course, these are largely interpreted to be formed by flowing water. This is one of the largest. I think it is the largest. Does anyone know what Marth means? March? No? It means Mars. Original, huh? So Mars Valley. Great. It's actually Welsh for Mars. And so Mars Valley, is a fantastically interesting place because it shows it shows a giant channel, and the important thing to note about the channel is that it didn't form in one event. What we see is that it formed in multiple events. That means that there wasn't just one big flood or one river that lasted for a while. It was multiple phases of activity. And its location is between an area of mostly higher ground and a large area of lower ground in the northern hemisphere of Mars. So Mars Vallis really represents an interface between two very different places on Mars, and it can record the flow of water over a long period of Mars's history. And what you're seeing here is a fly-through from the Mars Express camera, HRSC, and these white patches are clay minerals. These are exposures of minerals that are very bright in the visible, and that means that they reflect a lot of light, so they're easy to detect, but you can also identify them very well with infrared spectroscopy. The important thing about clay minerals is that they form in the presence of water, and so the fact that they're there in such abundance and in so many different layers throughout the vertical profile of Mars Vallis means that there was a lot of water over a long time in many different episodes. Clay minerals on Earth are associated with some of the evidence for the most early detections of Earth's life. So terrestrial fossils, the oldest terrestrial fossils we know about, are usually detected in association with clay minerals because of this water origin, and also because clay minerals, because of their mineral structure, and Susanna may tell you more about this, they can provide a basis to host nutrients. So, water-influenced landscapes. The second part of this is that we see a lot of ancient rivers. These are inverted channels. An inverted channel forms when a river is depositing sediment on its bed, and over time, more and more layers build up, but eventually the river stops. And then wind takes over, it erodes the beds, and that central deposit in the channel is left there because it's harder. It's lithologically a harder sedimentary rock. And so it's left while the beds are eroded away, and you end up with an inverted riverbed. So you see the riverbed elevated compared to the surrounding terrain. This is an example on Earth. This is called the Green River in Utah. This is a perfectly preserved inverted channel from much more recently than we think this area on Mars was formed. This scale is 5 kilometers here, so actually it's not too dissimilar. But see also what we see is that these inverted channels have many different branches, meaning that there were different parts of the river forming at different times. So this isn't, again, not just one dramatic flood that happened because, you know, some ice melted or because some volcano erupted and caused, you know, a giant ice sheet to melt and flow somewhere. This is sustained water flow for long enough to form different channels. So this period in Mars's history seems to be not so dissimilar from many features that we see on Earth. Another really striking example is deltas. Deltas are special because they form only underwater. Deltas occur when a river flows into a standing body of water. That can be a lake, or it can be a small sea, or even an ocean. And so when we see deltas on Mars, we know that at some point there must have been a standing body of water for that delta to form in. So this is very exciting because it tells us that not only was there standing water, and in this case it's in Ebberswalde crater, which I think was a candidate landing site for some previous rovers, and what we see is that it has an enormous number of branches. And if you were looking at a satellite picture of, you know, the Ganges Delta or whatever, you might see something that looks remarkably similar. We can zoom in on this, and it does in fact look very terrestrial with this coloration. But again, what we see is that this had to exist long enough that all of these different branches could form. And deltas do form slightly differently on Mars and Earth because the gravity is different. There are differences in what sediment sizes you might expect to fall out of the water suspension at different places, but that's a detail. But broadly, deltas form in mostly the same way on Mars, and so we can interpret them to try and understand what that river was like, what that standing body of water was like that it flowed into, and what that means for its habitability. The next part is mineralogy. We can see from orbit minerals on the surface, and these show up as essentially different colors, but you can map them in different ways. I won't go too much into the detail, but the point here is that since this renaissance in Mars orbiter missions in the last few decades, we've had the ability to map at quite high resolution. This is 18 meters per pixel in these pictures. The layers and what minerals they contain, or groups of minerals that they contain. And this allows us to try and deconstruct how they formed and at what time and in what sequence. Another important thing that's happened over geologic time is the erosion of Mars's atmosphere. I mentioned Mars used to have a magnetic field, and then at some point it stopped. And so that meant that a lot of things were then reaching the Mars's surface that were previously not. And not only the surface, but the atmosphere, which means that essentially the damaging particles that would erode the top of the atmosphere were getting through, and the atmosphere was being gradually stripped away. So let's go to the lab quickly. An important thing to know about this is that we can see the extent of that change and how much Mars's atmosphere has been eroded, because hydrogen, simplest element, one proton, one electron. But there's a heavier version of hydrogen called deuterium, which has an extra neutron. If you give hydrogen 1 and hydrogen 2 the same energy, then it's harder to move hydrogen 2 because it has a larger mass, right? And so hydrogen, H2O, 2 atoms of it and a water molecule. This implies that if you're throwing energy at water molecules in Mars's atmosphere, the lighter one is more likely to be pushed further. And broadly, this means that over time, when high energy particles hit light water, it gets split apart, and then the light version of hydrogen gets lost to space much more easily than the heavy hydrogen. Now, this difference is commonly referred to as the D to H ratio, deuterium to hydrogen. And on Mars, we can see that that's 5 to 6 times bigger than the Earth's, which means that the extent to which Mars's atmosphere has been stripped away and that water has been essentially removed from the system by breaking it down into hydrogen and oxygen. Hydrogen leaves, disappears off into space, and the oxygen, by the way, goes to the surface and reacts with things there, which gives you a lot of red-looking minerals. So this is one of the big reasons that Mars looks rusty. Okay, so putting this all together, we can try to plot Mars's history. And geologists like to refer to geologic timelines or epochs. On Earth, the earliest geologic time we have is the Hadean. That's just after Earth formed, when it was a giant ball of magma. And then we had the Archean, in which some of the earliest preserved traces of terrestrial life formed. And on Mars, we have the pre-Noachian, which is effectively equivalent to some of the Hadean, then the Noachian, the Hesperian. And you could notion that the start of conditions on Mars that were perhaps compatible with life started in the pre-Noachian. On Earth, we don't know, because much of this evidence has probably been erased, but these are the oldest ones we've found so far. But if you plot this over time, you see that an important environment for early life is hydrothermal systems. So these are places where you get heat and nutrients from volcanic systems that are entering water. And water as a medium is very good to allow interaction of organic molecules which react with each other and eventually get more complex, and it's believed eventually formed life. But the specific conditions under which that happened are really not yet clear. But in any case, this environment is the prime target. And so finding places where those environments may have prevailed on Mars is an important aspect of astrobiology. However, at some point on Mars, what we know compared to Earth is that the atmosphere dramatically changed, because perhaps the magnetic field was lost, the atmosphere got stripped away, and it went from something that was largely clement, perhaps had a thicker atmosphere, supported liquid water on the surface, to something that was very dry and exposed to ultraviolet, to high-energy cosmic rays, and other things. And so essentially this period in Mars's history, the Noachian, is the last chance and the most interesting target to look for preserved remains of habitable environments and organic molecules that might have been involved in what we call prebiotic processes. So I talk a lot about life, but the point is that the record of Mars's geology is very similar to Earth, up to a point, we think, and at some point it diverged, preserving that most ancient period, which we can now investigate, because we can uniquely get to it with robotic space missions. So one of the big questions in astrobiology is what is habitability? We have a rough idea of what the envelope looks like, but we don't know if it's like this, lots of standing bodies of liquid water with volcanoes everywhere and a thick atmosphere, or similarly a thick atmosphere but a kind of icy, mountainous, not very energetic environment. But whichever one is true doesn't really matter. The point is we can look at what's preserved to try and deconvolve what those environments were in this Mars world record. So to summarize, many processes that were important on early Earth seem to have also been active on early Mars. And early on in the history of Mars, there was definitely water, and it was episodically present. So it was kind of coming and going. There were dramatic events. There were some more low energy events, but they may have preserved or sustained some potentially habitable environments, which we can now start to pick apart and investigate, because they have not been recycled due to the lack of plate tectonics. So this is one reason why we think we can justify the scientific investigations on Mars's surface. I'll move quickly to talk quickly about what is life. When we talk about life, life is cells. Everything in life is contained in cells. And cells need water because various biological reasons I won't go into. But essentially all this to say is that there are some molecular smoking guns, or at least indicators, that we can search for based on what we know about terrestrial life. One of the interesting ones is what's called homochirality. And that's because biomolecules, everything that make up our bodies and all life on Earth, has two mirror forms of certain molecules. And life tends to use only one of them, but not the other. And it depends on the molecule. So for example, we use left-handed amino acids, but right-handed sugars. And this is a trace that we can look for in anything that's preserved. So, this bias, plus all of these types of molecules, sugars, phospholipids, amino acids, nuclear bases, pigments, we can search for those in the geologic record of Mars, if they have survived for billions of years after they initially formed. We're not sure of that yet. So we can also look for more obvious things, of course, and if we see a dinosaur bone on Mars, that will be a smoking gun and probably raise more questions than answer them. But we also need to be careful because there are delivered organics from space. Things arrive on meteorites all the time. We know for a fact that amino acids form out there in the universe. They don't need to be particularly in a special environment. They just form, and we get bombarded with them all the time. So this is a kind of organic background that we need to subtract from whatever we detect on Mars. So we're looking for places on Mars that might have looked like a hydrothermal setting under a lake or an ocean, and perhaps also organic molecules that are on particles that might have been deposited, on a river, a river bank, or at the end of a river in an estuary or a delta, indeed. And of course, clay minerals are the big pointer to those kinds of environments because they can only form where water has been present for a long time. So I will jump ahead to talk about the Rosalind Franklin mission, which is what I work on, amongst a few other things. It's a rover. We're launching in 2028, arriving in 2030. There are 8 science instruments and, uniquely, a drill that can go down to 2 meters. Plus, 3 of those science instruments are inside the body of the rover, and they do some very special stuff, which will help us characterize and detect potential biomolecules. I want to mention Rosalind Franklin. Rosalind Elsie Franklin was a British chemist, the namesake of the mission. She and her postgrad student, Raymond Gosling, produced this diffraction pattern, which was helped to develop a chemical model of DNA. But the Nobel Prize in Physiology and Medicine went to Watson, Crick, and Wilkins, and that was 4 years after she died, unfortunately. But at that time, there was no prevention of the Nobel Prize Committee awarding prizes posthumously, but because of the era, unfortunately, that didn't happen. So now it's important to recognize those successes, and hence we named the mission after her. Interestingly, her brother was so inspired by her work that he named his daughter Rosalind Franklin, who is still alive and interested in what's happening with the Rosalind Franklin mission, so much that she came to visit us. And so here is the niece of Rosalind Franklin with the Mars robot, Rosalind Franklin. But more about the rover. It's really a special machine, and I could speak for another 3 hours about it, but I won't. And I'll choose 3 things to tell you about the mission. So here you can see a bunch of tests going on, but I'll address those as I come to it. The first important thing, we can drill. And we have this fantastic drill, and here's a kind of engineering blowout of it. The important part of this is that it has drill rods that can be assembled successively to drill down deeper and deeper. And this gives us access to the subsurface, which no other mission has so far been able to do. Why is that important? Because if we talk about amino acids, which I've done quite a lot so far, we can determine how far down we need to go to reach somewhere where enough amino acids would have survived such that we could detect them with the instruments on the rover. And so amino acids, we know, being the building blocks of what we know about, they're about 2/3 of a cell by dry mass. And they also preserve this homochirality, the chiral molecules, the left and right-handed versions. So they're really good, representative molecules to use when we're testing what we should be sampling and what we could detect. So these lines are for different amino acid soups. And essentially what we learn is that we need to go down to about 2 meters is a good maximum limit, but 1.5 would be okay. Because these molecules degrade quite a lot near the surface because of everything I mentioned earlier. But they survive pretty well once you get past a certain point, and that's the area that we want to target with the drill. So this is why we have a drill. Works well. We've done lots of tests, and there are some fantastic videos. You can take a look on the ESA website. I'll jump ahead to the next fun thing, which is the payload. And when we say the payload, we mean the scientific instruments, and there are 8. They come from teams based all over Europe and also the US because of the NASA contributions. There are 5 which do surveys. Let's say they're the instruments that look at the surface and the subsurface, the environment. And then there are 3 dedicated to analysis of samples, which are acquired by the drill. And those are inside the body of the rover. There are some videos to show you quickly here, but essentially the process of operations is that we go to a new place, we start to investigate it with the survey instruments. We have some fairly unique mobility capabilities on the rover, and one of them is this called wheel walking, where it moves kind of like an insect, and this is to allow us to traverse soft, sandy material that would otherwise be too difficult to navigate. So if we get somewhere where we see the wheels are sinking, we can essentially start walking to get over it. So that's a nice to have. We may end up using it, but let's see. And this allows us then a bit more flexibility in accessing places that might be of interest that are otherwise difficult to get to. So this is something that was developed uniquely for this mission. And then when we access a new site, we take a panoramic survey using the various cameras, perhaps with some mineralogy with the infrared spectrometer. ENFIS, by the way, ENFIS, also a Welsh word, means rainbow. Wonderful, it's a spectrometer, that makes sense. And once we have these kind of contextual bits of information, we can then plan what to do in terms of where do we want to perhaps drill, where do we want to take a sample, what is the highest priority in terms of analysis. So that's the overall process. Once we get to a place, we survey it much more closely, and we have an instrument specifically designed to look at textures very, very close up to try and understand, the grain size distribution, how are the minerals distributed, and what's the material like if we were to try and drill it. And so this is the kind of second phase of the site survey before we choose somewhere to drill. Okay, and you saw also we can move sideways, which is also very convenient. Okay, so then we drill, we take a sample, and once we take a sample, it gets deposited in what's called the analytical laboratory drawer. This is the little tray where you drop the sample out of the drill, and it gradually gets retracted back into the analytical laboratory drawer. This is the thing inside the rover which has the three instruments that can characterize, ultimately, potential organic molecules, or potential organic molecules with a biological origin or not. But in any case, this is a very unique special source that the rover has. This is a very complicated thing, but essentially we crush the sample into a powder, we put it in a tray, and then the tray moves under three different instruments to be analyzed, and optionally some of the powder can be put into one of these little ovens where we do a whole bunch of other clever chemistry to analyze the sample using a mass spectrometer instrument. So that's the short story. The container is basically the size of a thumbnail like this, and so we're putting crushed sample into here, but then if you zoom in very closely, you can analyze it with these various instruments in different places and do some very clever chemistry, which I won't claim to know everything about, but I'll do my best. But the upshot of this is that after all those things are done, we get what's called a mass spectrum of the large organic molecules, plus the geologic context that we learned from analyzing the site and from analyzing the sample with some of the instruments. So if we were to detect molecules that we thought were involved with life, we would probably see something that looks a bit like this, an abundance of things that are in very specific places. Because we know there are a bunch of organic molecules out there in the universe which are constantly bombarding the planets. But the ones that are involved in life are very specific, and they might leave some signatures that we can look for. The instrument that we use, MoMA, can see this whole distribution. So that's essentially how it works, and the big bonus is that we can also see the chirality distribution. So if there are preferential traces in right or left-handedness, we should be able to see those. Okay, I'm going to skip through because I've used a lot of your time. But in any case, this is essentially where we will be when we have those results, and it will be a challenge, but we're excited about doing it. I quickly want to mention the landing site. We chose somewhere which we know to be ancient. It probably formed when Mars was at its most habitable, arguably, and there are a few places that meet those criteria, but this one was selected because it fit the bill, and in fact we see right in the middle of this Noachian period is where we think it most likely formed, and it has a lot of clay minerals, which you remember are very important for the origin of life. Its history is pretty dynamic, but ultimately we've got a pretty good idea after having studied it for probably more than 10 years now. And this is achieved by, a team of people working diligently, using all the orbital images we have, mapping specific things. And in fact, I just want to make a plug that one of the lead authors of this geologic map, which is shown out there, by the way, on one of the poster boards, is Peter Forden. Dr. Forden led this work for, I think it took 4 years from start to finish to produce this geologic map of the landing site. So we're very, very proud of that. And you can look it up online, but there's a wonderful video showing the full map. Okay. When we do science operations, we're going to have to try and interpret everything we see at the landing site to make the best choices. And we don't expect it to be easy, but we have some robust processes and a team who have to be trained and have been trained to do so. And we do this through simulations. This is the Rover Operations Control Center in Turin, in Italy. And we have a bunch of tools and very dedicated people there. We run simulations to learn how to do the best science we can possibly do. There are actually 2 rovers, by the way. Rosalind Franklin is the one that we will send to Mars, but she has a sister, Amalia, who we use to do testing of all of the things that we want to try on the real one, but we don't want to wear out the real one too much before we send it to Mars. It will be a lot of fun when we finally get to it, but unraveling Mars's geologic record, I think, is really the goal of this. It's not just to play with robots, although that is a fun part. But I want to leave you with one final thought. You might know about the Drake equation. This is an equation that tries to quantify the probability of finding a technologically advanced civilization in our galaxy. And you can formulate it in lots of different ways, and many people have, but this is one of them. And there are a bunch of factors which are probabilities, and they tell you essentially how likely is it for each of these steps to happen. So we start right at the start, rate of formation of stars in the galaxy. Okay, to have life, you probably need a star with a planet or more around it, and you have to have a bunch of other things that happen along the way until you get to some civilization that looks a bit like us. And you also have to consider how long those civilizations might be active if you want to detect them. What we now know since 1995, when the first exoplanet was discovered, that is the first planet outside our own star system, is what fraction of all the stars that we see have planetary systems. Turns out it's most of them. That was a big step change in our understanding of this equation. How many planets does each of those systems have? We also know that from lots of our exoplanet missions. But the thing that Mars offers us very uniquely in our own solar system is what is the fraction of planets on which life actually appears. If we detect life on Mars, or evidence that life once existed on Mars, by unraveling the geologic context, the geologic record, or if we learn that it definitely didn't happen, that's a huge leap in understanding in what is the probability of this happening elsewhere in our own solar system. Think of the oceans of icy moons, or in other star systems. So I'll leave you with that, and I want to thank you so much for taking yourselves here on a Sunday. It's been a pleasure.
Thank you so much, Elliot. That was fantastic. A whirlwind tour through everything ESA does all the way to Mars. Thank you so much. I am sure there are many, many questions. We have microphones around. Please do use them so everyone can hear what you are asking. There they appear. Do we have a first question somewhere? And we are taking questions from people of all ages and lengths. So, any questions? One is up here. First row.
How large is the Mars rover?
Yeah, a little bit taller than me. So you see this mast just up here in the middle, that's about this high. So it's kind of like a big go-kart. Yeah.
Can go along here.
Just asking, how is it powered? It looked like it had solar panels on it. Is that right?
Yeah, it's solar powered, that's right. So we don't have any radioactive isotope power units on it.
Does that mean it will go for many years, hopefully?
Yeah, indeed. The design as it stands, we can do everything that we plan to do. We have a kind of reference mission that we design the whole system to, and the panels give us a lot of robustness. It changes with season, of course, because if there is more dust in the atmosphere, we get less sunlight, and obviously during the winter we get less sunlight. So we'll have busy high energy days and days where we can only do a few hours of operations during the winter. But overall, it just keeps going until something breaks.
Thank you.
Let's hope it is as long as, say, opportunity. Okay, any other questions in the room? Well, while the microphone gets up there, what is the thing that you personally hope to find?
Yeah, that's a really good question. I honestly don't know, and I don't want to have expectations for them to be changed, because we're always going to be thrown a curveball. That said, I think what I would really like to find is clarity.
That's a very good answer.
On a lot of unanswered questions that we have.
Yeah, so I guess the microphone has arrived up there.
Do the rovers have any sort of end-of-life plan?
Well, we can't bring them back, if that's what you mean. But I mean, yeah, there are procedures on what you do when you shut it down, for the last time. But it's pretty basic. You want to leave it in the best possible state you can. If someone were to come back in the future and investigate it for a kind of post-mission assessment, but we don't pay too much attention to that. One thing that is relevant, I think, to say here is that all missions have to comply with what's called a planetary protection protocol. And that might not be what it sounds like, but it's to make sure that the Mars environment is preserved so that we don't contaminate it with our own spacecraft. So it's thoroughly cleaned before we send it. So anything we send to Mars is not going to bias future science that's done on the surface. But essentially at the end of the mission, because it's on the surface and it's not in space, we switch it off. But I expect, and I think it's true, that we can always switch it back on. So for example, if we have to stop it for some reason, we can disconnect the battery, but leave on a kind of emergency receiver so that we can tell it to reconnect the battery. If there's a global dust storm and we know we're not going to have enough power for a few weeks, we can turn it off and then repower it up again afterwards. So I don't like to think about turning it off forever too much, but yeah.
So it's scientific life is potentially unending. It will go on as being an object of interest and possibly materials of use in the future for those who might come, or those creatures or machines that might come and find it.
Sure, I think so. One other interesting thing is that there are a few consumables in it. So if you remember from the slide with the interior instruments, it had that little carousel of cylinders. Those are little ovens. We have a limited number of those. So in terms of doing the science, we can only do a fixed number of analyses with that instrument. But all the other ones can go as long as they last.
Okay, the microphone is up there, I'm learning.
Is there any intention of bringing back any of these samples to Earth for further analysis?
Yeah, it's a good question. That's a whole other talk. Yeah, well, as of right now, there have been for decades discussions about bringing Mars samples back. And the best cache that we have is in Jezero crater, collected by the Perseverance, the Mars 2020 mission. And so the Mars 2020 mission was always intended to be the first mission in a Mars sample return campaign. So there are 10 sample tubes deposited in a useful place where we think we could retrieve them in the future, in Jezero crater. There are a larger number of sample tubes filled with interesting material that has been collected at Jezero on board the rover, which could be then either transferred to a return mission or left on the rover if we retrieve the backup cache of 10 tubes instead. But right now, Mars Sample Return is a partnership between ESA and NASA. There are some uncertainties about whether NASA will be able to support it in its current proposed form. That's happening, in the last few months, this has all kicked off. So it's uncertain, but we're in a good place to be able to return them. ESA is developing the return orbiter, and that's in a state where we're ready to start building the real version that we sent to Mars. And we also contribute to a lot of parts of the receiving end, so that when the samples get back to Earth, we contribute to the facility, which would then be used to contain the samples, to unpack them, to catalogue them, and do some of the analyses on them. So yes, but it's complicated.
There is a question here, and then there is a question up there.
I'm just wondering if the effect of Brexit is impacting the UK's partnership into the future. And as a long-term researcher into wind turbines, I was wondering about including a foldable wind turbine, whether the atmospheric density on Mars might be suitable for wind.
Oh yeah, that's a good question. So for the first part, the only part of ESA that Brexit affected were the programs which the EU funded. So there were a few projects which directly received EU money, where they said, look, UK is now not responsible for paying into these, and so we can't have UK involvement. But it was a very small number of things. Overall, ESA is an independent organisation. It's completely international. We have member states that are decoupled from everything else. And there are many similar organisations like, Council of Europe, European Courts of Justice, NATO also. So it kind of stands on its own in that sense, and Brexit hasn't had a big impact there. For wind turbines, that's an interesting question. I mean, drones have been used. The Ingenuity helicopter on Mars 2020 has been a fantastic technology demonstration. And there are many studies that I'm aware of to send drones again to Mars. And so why not, if used as a lifting device, could they not be used also to impel power generation? I don't know. I haven't seen studies on it, but I'd be interested.
We have a question up here, and then if you could go over there.
Hi. I was wondering who comes up with the names for the galleys and the craters and everything on Mars, and then are they universally used worldwide by everybody? Are the same names used, or do each country use their own
Sorry, I'm still looking
version?
for who's holding the mic. Can you raise
Very up there.
Ah, hello. Sorry, I didn't see you. Yeah, that's a great question. It's for the most part, it's the International Astronomical Union, the IAU, and that's the international body that is responsible for authorizing the names of celestial objects. So when we discover a new thing, a proposal has to be made to name that object, and there are certain criteria that have to be met. The landing site for ExoMars, for example, Oxyplanum, didn't even have a name until 2019, I think. So that process was something we got to see happen in real time almost. There are, however, local, depending on the mission you're in, local designations that people use. So, for example, if you saw Susanna's talk on Perseverance, I expect there are a bunch of informal names used for certain outcrops or rocks or whatever. And that's something where you're discovering so many new things. There's just no time to submit official proposals. But there is also, I think, a size limit on the feature that you're allowed to propose to be a new object. So, and it's a few kilometers. So, I hope that answers your question.
Okay, I think we have two questions down here. Can you just raise your hand if you have the microphone? So these two, and then I'm taking this up there. Okay, go ahead.
Hello. Some years ago, there was a marvellous exhibition at the Hayward in London, which was photographs from the moon expedition. Just absolutely mind-blowing. It was a fantastic achievement. Looking back with hindsight, though, perhaps it didn't happen how we would have wanted it to happen, because it very much broke down to USA versus the Soviet Union. You can only speculate. If it had been a joint venture, would politics today be a bit more peaceable? But so what can you do? What might you do at the European Space Agency as we move towards that day when we go to Mars? What can you do to try and make sure it isn't USA versus China versus Europe versus India, any other players who come onto the field?
Yeah, well, I mean, as you can imagine, there's been a lot of discussions about what does ESA do in reaction to the shifting geopolitical situation in recent years. And you might know that the ExoMars mission was already suspended and reformed once after the Roscosmos partnership broke down in 2022. We repartnered with the US. And now we're on track. But I think what ESA is focused on is, first of all, maintaining all of its commitments. So if we make an agreement or a cooperation agreement or a study agreement or anything like that with an international partner, we stick to it. We don't want to pull out because of politics. And because there are 23 member states and some other states who participate in different ways, I think for ESA we're seen as a much more stable entity because we don't have national priorities. We incorporate everyone's national priorities from all of the member states. So it's more stable in that sense. And so I hope that larger international partners like the US, for example, see us as a more kind of resilient partner to political events. What can we do? I mean, be an attractive partner and try to collaborate scientifically. I mean, what we see throughout all of these changes in mission architecture and partners is that the science is the thing that is kind of agnostic to those political changes. And we still have the same, science collaborations that happen and interest. So I think science is one of the big keys to bridging those events that's more stable in the long term, because people are not pursuing some political goal, they're just pursuing learning about something.
Okay, I just got the flag warning, so I'll take this question, I'll take the question up there, and then just one more. So, go.
You mentioned the difficulty with which astronauts could operate on the surface of Mars. ESA is doing pure science at the moment, but there is a man already heaving enormous rockets into the sky with a view to colonizing Mars. Politics notwithstanding, just how far apart from the pure science that you are investigating right now is his aspiration towards implementation? I was fascinated to see the word gypsum on one of your slides. How might those two bodies, ESA and Elon Musk, actually work together to produce the circumstances where man could operate on the surface of Mars and indeed flourish? Are we talking centuries apart?
Yeah, well, as with most things, it depends on the political will and the money. And usually the money is a function of the political will. So I think in the case of Musk, indeed, he has very ambitious plans for SpaceX. There are a number of hurdles to overcome. Now, getting a rocket there is comparatively easy to sending a human there safely. And that's the bridge that I think that has to be crossed. I mean, ESA and NASA and probably other nations have in their long-term plans to send humans to Mars. That's a fact, and that's a roadmap that we work towards. And there are technology developments along the way to try and make that something that is safe and that produces the right scientific return. So things like developing, the proper filtering for spacesuits, having a spacecraft that's robust for a very long journey, and most importantly, having the habitats and all of the other infrastructure that needs to exist on the surface before you send people there. My expectation is that those technology development and kind of proving programs will have to last for decades before anyone feels safe sending an astronaut. And of course, there will always be people who are willing to be the martyr for the cause and go to Mars without those safety factors considered. But I don't think ESA or member states would endorse embarking on that without a guarantee of the astronaut safety. So I agree. It's great that SpaceX is providing a lot of inspiration, and in fact, SpaceX is very much a commercial partner for NASA because NASA procure a lot of rockets from SpaceX. With NASA, our current partnership on the Rosalind Franklin mission, in fact, we invite NASA, and they have offered to provide a launcher, so we would be using a US rocket, perhaps from SpaceX. So it's part of the space economy, but humans to Mars, there are some bridges to cross, but we're on a path to get there.
Okay, we've got the microphone up there.
So you're, I understand, exploring for items we know about already, minerals, water, things like that. How would you ever find if there are items there that we don't know about yet in our universe? And then lastly, have you got a protocol if you meet a Martian?
Yeah, sure. Sure. Yeah, well, so one thing to think about is in astrobiology as a field, there are new scales of confidence that are being developed and iterated. And this is something in the community that, it's kind of the first order of business. How do we know if something is an original non-terrestrial, biological molecule? And it turns out it's very hard to tell. And it's very hard to tell in particular because you need robust enough statistics. And if you find something that is that special, it's quite hard to gather statistics because you probably only have a few measurements. And so one scheme that I'm aware of that exists has something like 9 levels of confidence. So you make an initial detection of a feature. Okay, you probably encounter a few of these, every few days. You're like, oh, okay, this is I don't know, some organic molecule that, like it's a benzene ring or something. I don't know. I'm not an organic chemist, but then, okay, so how can that form? We need an independent verification that that detection is real and not a false positive. So we need another measurement, perhaps a few more, depending on the instrument, to get the confidence that it's a real detection. Then you can say, okay, how does that molecule form? These are the ways that we know it forms, and there are probably others that we don't know about. What level of probability can we ascribe to the fact that it could be something, that came from a different biology? So, and then there are 6 more steps. So so the point is, it's going to be very difficult, I think, without a very obvious smoking gun, which we might not know what it looks like, to have any confidence that something is of extraterrestrial origin. And there are protocols, in fact, but they're not as dramatic as you might think. In preparation for the Mars sample return with NASA, there are working groups trying to decide, okay, what is the process to establish, first of all, the level of organic chemistry that already exists, that we know exists out there in the universe, that is constantly bombarding planets. How do we confidently set that baseline to know when something exceeds it? And that's actually one of the hardest things to do. And then once something exceeds it, there are a few obvious things that you could look for. If you find DNA, your first question is, okay, well, this is probably contamination. How do we prove that's not contamination? That's also extremely difficult. So, those steps are not about how do we say hello in Martian. They're more about how do we really verify this isn't just us not understanding something that we're seeing.
Okay, and I think I use this last word about how do we say hello to a Martian as we need to say another hello to a Martian that's actually here, and it's in the courtyard down there. And because we stop at 1600 today, if you want to have a chance to still walk around, I will stop it all here now, but not before saying a very, very warm thank you to Dr. Elliot Sefton-Nash from ESA.